In this Level 2 course, you'll be introduced to the air intake and filtration system. You'll also understand efficiency and test standards, and you'll learn about contamination and servicing practices. Let's begin with a review of the material learned in the Level 1 Fleet School Air Filtration module. First, we learned that the importance of air filtration is to remove all of the contaminants from the air before it enters the engine, protecting your engine and maintaining performance. We also learned about dust, restriction, and air filter lifetime. Specifically, as the air filter removes more contaminants, the restriction increases. The restriction makes it difficult for the engine to breathe. We also learned the filters are selected according to the working environment to maintain engine performance. In Level 1, we explored several air filtration techniques. We learned about pre-cleaners, filter elements, and restriction indicators. Finally, we were introduced to 3 FleetGuard product solutions: Direct Flow, Magnum RS, and OptiAir. After completing this course, you'll understand the air intake and filtration systems used on today's engines. You'll learn about the efficiency and test standards established to help protect your engine. You'll be introduced to the types of contaminants that can harm your engine. Finally, you'll learn how to service your air filter. Let's begin with a discussion of air intake and filtration systems. Modern engines are subject to ever-increasing performance expectations and reduced emission output. The air filtration systems that service these engines have to keep pace by meeting the engine's air filtration challenges. In a modern engine, performance and fuel efficiency can be boosted by adding turbochargers, compressors, aftercoolers, intercoolers, and high-pressure fuel injection systems. These enhancements increase the need for clean air and low restriction to optimize engine performance. We're going to discuss a few of these methods in more detail in a few minutes. It's important to understand that forcing more air into the engine increases power output. Injecting pre-compressed air prior to piston compression stroke gives the engine more oxygen for a bigger bang. In the example shown, the air entering the engine is naturally aspirated. As it moves through the system, it is supercharged and then turbocharged to provide the most oxygen at the intake stroke. The chart provides an example of how much extra horsepower is achieved from turbocharging and further aftercooling an engine. The 4BT turbo model produces 38% more horsepower than the non-turbo 4B. The 4B is a naturally aspirated engine. The 4BTA turbo and aftercooled engine produces 58% more horsepower than the 4B. The 4BTA also produces 14.3% more horsepower than the non-aftercooled turbo 4BT model. Turbocharger. The air intake capacity of a diesel engine can be greatly increased by the addition of a turbocharger. A turbocharger is a centrifugal air pump or blower driven by exhaust gas. It fills the engine cylinders with fresh air at higher than atmospheric pressure. More air means more fuel can be burned. By increasing the amount of fuel injected to a corresponding increase in oxygen, more horsepower is achieved. Most turbochargers are similar in design. As soon as the cylinders begin to fire, expanding exhaust gas flow causes the turbine to rotate in excess of 100,000 RPM, or about 35 times faster than an electric motor, its speed varying with engine speed and exhaust pressure. The exhaust gases exit through the exhaust pipe and muffler. Because the turbocharger rotates at extremely high speeds, lubrication and cooling are essential. Oil is pumped from the engine to the moving parts of the turbocharger, and in some instances, extra cooling is provided by adding a coolant water circuit. Intake air cooling. Steps in air temperature reduction. A critical area in the air induction system is intake air temperature. Intake air heated above 40 degrees centigrade, 104 degrees Fahrenheit, is less desirable for combustion since it is thinner and contains less oxygen by volume than air temperature between 0 degrees centigrade, 32 degrees Fahrenheit, and 40 degrees centigrade, 104 degrees Fahrenheit. Exhaust gas through a turbo housing reaches temperatures above 750 degrees centigrade, 1382 degrees Fahrenheit, and intake air can often be heated to temperatures above 150 degrees centigrade, 302 degrees Fahrenheit, too warm for even the turbocharged engine to be delivering to the combustion chambers. Adding an aftercooler can cool the air delivered by the turbocharger to 100 degrees centigrade, 212 degrees Fahrenheit or less. The air-to-coolant aftercooler is a heat exchanger and works much like a coolant radiator. Hot air from the turbocharger flows over the heat exchanger core tubes that has coolant running through them, as shown below, and the heat collected travels in the coolant to the radiator to be dissipated. Another method for cooling the air before it reaches the compression chamber is an intercooler. It's placed between the turbo air outlet and the engine intake manifold. Unlike an aftercooler with air-to-coolant design, the intercooler runs the compressed air through the core tubes and not coolant water. Air flowing over the tubes of the core, aided by the fan and its placement in front of the radiator, allows for air-to-air cooling. The intercooler works like a coolant radiator, except that it has the hot air from the turbocharger running through its core to the engine instead of coolant water. The heat is radiated from the hot air to the atmosphere through the core, in the same way that heat is radiated from coolant through the radiator. So, knowing about the enhancements that make modern engines more powerful and efficient, you need to understand how to protect your engine. To receive peak performance and life from the engine, the air the engine breathes must be clean. And if dirt or other contaminants are allowed to pass through the air intake system and into the engine, problems will develop. Dirt that gets through an engine's air filter system enters the combustion chamber, mixing with fuel and oil on the cylinder walls. It then passes to the piston rings, ring grooves, and crankshaft. This dirt scores cylinder walls, rings, and bearings, and gums up rings and valves and blocks off oil passageways. Dirt in the system results in wear to these parts, causing particles from the metals it removes to further promote wear and tear on the engine. As a result, the engine loses power from compression loss and begins using more oil. The life of a diesel engine is directly related to the amount of time that it takes for that diesel engine to ingest between 100 and 200 grams of fine dirt of various size particles, as proven in a test run by the Cummins Engine Company years ago. Cummins demonstrated how quickly an engine could be destroyed by gradually adding a small handful of dirt that destroyed a Cummins NH220 in less than 8 hours. With a single-pass air filtration system, its one filter provides only one chance to remove dirt particles before they enter the engine. That filter has to be working properly. Air and dirt enter the filter, but only clean air can pass into the engine. Generally speaking, heavy-duty filters must be designed to meet specific requirements of the systems that they serve. Filters on all systems must provide optimal efficiency and capacity, and all should function to reach the same result, reduce wear and extend the life of the engine. To perform the function of reducing wear and extending engine life, the air filter must filter 100% of the pre-combustion air at a very high total efficiency. Remove as much dirt of any and every particle size it can. Maintain sufficient airflow to the engine. Get it right the first time with a single pass only. So, I have a question for you. What is the micron rating of air filters? The answer is, there isn't any. So how are air filters rated? Air filter efficiency rating is different from other filters. The ratings don't refer to the efficiency of particulate removal limited to any one specific size of particle. The filters are rated by total overall efficiency using a standard test in accordance with SAE J726C. The test dust is of various sizes and mineral types that best represent airborne particulate. Therefore, reference to any single particle size in microns is not relevant. SAE J726C is a world standard, and it uses graded dust of various sizes and types to measure efficiency. The test requires a minimum start-out efficiency of 99.2% and 99.9+% removal efficiency at the termination of the test. The types of contaminants likely to enter an engine vary with differing environmental conditions. On the road, the most problematic contaminant is the soot from exhaust systems, although the air may look clean. Let's talk about contaminants in more detail. We'll begin by discussing dust. It may seem counterintuitive, but the dirt cake formed on a filter can actually lead to better efficiency. Some forms of dirt, particularly the coarser variety, provide extra air passageways. In the diagram, you can see the air passageways in the paper medium, but even as dirt particles build up, they form a cake that provides extra air passageways. A dirty, dust-loaded element does not necessarily require replacing. Surveys have shown that filter changes based on how a filter looks often result in the filter element being changed too early. By contrast, exhaust soot is bad for the filter. Soot or exhaust contamination plugs an air filter quicker than anything else. Airborne soot particles mixed with unburned fuel, varnishes, and tars, for example, create a paint-like consistency that quickly bridges the pore entrances of the media. A truck idling alongside another for a period of time at a truck stop can be all it takes to plug the filter. Engines running in confined spaces with poor ventilation or that draw the air close to their own exhaust outlet or a leaking exhaust system can be affected. When a filter is coated with soot, the resulting flow restriction occurs with little weight gain to the element, making it hard to determine whether the filter needs changing or not. Soot and unburned fuel damage a filter, and the impact of sudden plugging is severe. Smoky exhaust gas plugs air filters very quickly. An air filter element exposed to a sudden rush of dense engine smoke can suddenly plug, producing a severe pressure drop spike across the element that can exceed the collapse strength of the element before engine stall. Under some conditions of high inertia, when the filter is suddenly plugged, for example, as the engine is starved of air, the element can collapse or the media can rupture. So, how can you tell if a filter is operating efficiently? Let's do a visual comparison. Here you can see two distinct forms of contaminant. Understand, though, that the difference is not always this distinct. These contaminants can be, at times, mixed together. On the left is a filter covered with a dirt cake from dust generated by an off-road environment. The filter would appear to be totally clogged. In this environment, it would be best to add a safety filter in addition to the primary element. On the right is a filter coated with exhaust contaminant, primarily carbon and unburned fuel, as is common in on-road environments. To the untrained eye, the filter looks unclogged and fully functional. On-highway vehicles and some power units working in clean environments, due to the low level of dust encountered, have mostly primary or single-stage filtration adapted without the additional safety element. There are three levels of filtration: light or normal duty filters, a paper filter element in a simple housing to provide single-stage filtration. Medium-duty filters employ two filtration stages. The first cycloid stage, removing a large quantity of dirt before it reaches the primary element. Sometimes a safety element is also fitted inside the primary element. These cleaners generally have dirt holding capacities of at least 10 grams of coarse dust per each CFM of airflow. Heavy-duty filters employ two filtration stages, similar to the medium-duty cleaners, but are generally designed with more effective first-stage separation and larger second-stage primary element. Heavy-duty air cleaners generally have dirt-holding capacities of at least 25 grams per each CFM specified airflow. In air filtration, seeing is misleading. Here's a typical example of how a first impression based on weight and amount of contaminant can be misleading. On the left, you see a filter that's loaded with 0.7 pounds, 0.3 kilograms of exhaust contamination. This filter is fully plugged at plus 25 H2O. This filter should have been changed much earlier. Just looking at the filter, though, it looks okay. On the right, you see a filter that's contaminated with 4 pounds, 2 kilograms of dust and is still moving air through at 12 H2O. This filter is only half restricted and still has life available. Look at the filter. It looks fully loaded, but it's actually okay. It just has a desirable dust cake. So you really can't tell when to change an air filter just by looking at it. So, what about servicing? How can you tell when a filter is at the end of its useful life? Unlike other filters on the engine, the contamination encountered by air filters is unpredictable. Atmospheric conditions are forever changing, from dry to wet, to dusty, to clean, to smoky exhaust. You get the idea. OEMs can determine at least a rule of thumb calculation for filter change intervals based on the fluid type used, engine load, and general engine contamination buildup characteristics. Service intervals for air filters cannot be calculated this way. Maybe you're thinking you can simply establish a set service interval based on time and service, but air filter life is not time predictable. As we've discussed, there are too many variables to be able to accurately set a time interval for filter replacement. We touched on this topic before, but air filter efficiency increases over time. 75% of all dirt that passes through the filter will do so in the first quarter to a third of the filter's service life. The air filter efficiency gradually increases to the end of the filter's life, getting close to 99.9% efficiency during the last two-thirds of its maximum life. As you can see in the graph, at the beginning of its life, the filter has the least restriction, but also the least efficiency, letting the most dirt pass through to the engine. Toward the end of its life, it is the most efficient. Changing the filter when it's in the early stage of flow restriction due to contamination buildup causes the engine to run with lowered air filtration efficiency. Changing the filter too often not only increases the cost of consumables, it can also be causing more engine wear. In this example, we're looking at a new element with a filter efficiency of 99.5%. Of the 100 pounds, 1 kilogram of dirt that enters the filter element, 0.5 pounds, 5 grams, passes through the filter and enters the engine. This is a massive 4 times more dirt than gets through as compared with a used filter with a final efficiency of 99.9%. Now, let's compare a used element that has attained a filter efficiency of 99.9%. Of the 100 pounds, 1 kilogram of dirt that enters this filter element, only 0.1 pounds, 1 gram, passes through to the engine. Used elements, those that have been in service for a while, pass 80% less dust than the new elements. This is a powerful reason to use the filter for its entire service life and not to discard it too soon. So, if you can't look at a filter and know when to change it, how can you tell when it needs to be changed? Change the filter based on restriction. To do that, you need to install a filter minder or restriction indicator. Cummins Filtration offers several options for measuring filter restriction. The first is a direct mount restriction indicator. This unit is mounted directly on the air filter. The second type is a remote mount indicator. You can mount this indicator in the most convenient spot in the engine compartment. There are 2 versions from which to choose based on your particular engine. Finally, there's the dash mount indicator. This unit is the most convenient, giving you a constant visual indication of remaining filter life. It is easily installed in the cab and is quickly visible at all times. When servicing your filter for best results, install an air restriction gauge to automatically and continually monitor the condition of the air filter. The air restriction indicator measures the vacuum in the inlet manifold and indicates the level of blockage in the air filter. When you change the filter, it can be reset for a new round of measurements. Most air filter housings have pre-existing connections that allow for easy installation and use of a restriction gauge. Using a restriction gauge improves your total cost of ownership by allowing you to use your filter to the very end of its life. Now that you've completed the Level 2 Fleet School Air Filtration module, you should know about the air intake and filtration system. You should understand that air intake and filtration systems work together to ensure optimum engine efficiency, low emission, and reliable operation. You should also know about efficiency and test standards. You should understand that there are no second chances in air filtration, and that air filter efficiency and test standards ensure that air filters remove contaminants the first time, every time. You should have a working knowledge of the types of contaminants.
You should know the difference between dirt and dust, which are coarse, bulky particles, and soot and unburned fuel, which form thin layers that block the element quickly. Finally, you should know when to service an air filter, namely when the filter is blocked, not when it looks like it's blocked.